some fractals.
And those are some. Oh,
Which is other.
okay.
Matt, why isn't it working? Okay,
I
wait.
was taking girls.
One minute
left.
Okay, I'll just go from over here.
Okay.
So these are some examples of fractals. That is actually some kind of vegetable that I don't actually know what it is. Maybe. And that is a tree. So.
Is it a real tree or is it a
It's a real tree.
fractal trees?
Trees are very similar to fractals because they're branches cut. So a fractal is a never-ending pattern that repeats itself at different scales, which is called self-similarity. So you can see, wait, no. It just keeps on zooming on forever, and it's the same image over and over and over again, just at smaller scales. So this is one of the most common fractals. It's called Sierpinski's triangle, and it's made by taking connecting the midpoints of each side of the triangle and taking out that center triangle, and then just keep on doing it over and over and over again until you get a lot of cutout triangles.
So this is a Pascal triangle, and if you color all the even number in blue color, it's actually the Sierpinski triangle.
So these are some calculations for Sierpinski's triangle. To find the number of triangles removed after a certain number of steps, use a sub k equals 3 to the k minus 1. And finding the number of triangles removed after a certain step number is s sub k equals 3 to the k minus 1, and then all that divided by 2. And the last one is for finding the area of the remaining triangle after a certain number of steps.
Okay. Fractal dimension. So this is a picture of some dimension we know. A point is 0 dimension, and a line is 1 dimension, and the square is 2 dimension, and the cube is a 3 dimension, and it's 1, 5. But fractal dimension, it's not a whole number, so it can be like 1 point, like half or something. And I'm gonna show you how to calculate fractal dimension. So let's begin with the line, and and you remove the center of the line and connect two that's all equal to each side. Okay, then you break each line into the same thing. So that then you break each line to the same thing again and again. And this is the function of fractal dimension. So log of numbers of the similar pieces over log of magnification factors. So let's go back to this picture. So here it's 4 parts of similar pieces. So log 4 over, and because you're cutting each line in 1/3, so it's log over 3, and it's equal to 1.26. So that's the dimension for this picture. So if pretend we don't know a cube is 3-dimensional object, so if we break each line in half and so we can make a like smaller cube, but it's similar. So log 8 over log 2 is equal 3. So we know it's the 3-dimensional object. So I have a question for all of you guys. So how can we calculate the dimension of Sierpinski triangle? You guys know? breaking it into half. So 1, 2, 3. So there's 3 similar triangle. Then over 2. So that's the dimension for the Sierpinski triangle.
When it's broken into that number of triangles.
Yeah. Okay.
So fractals have a lot of real world applications, including in cancer, because they figured out that the dimension of cancer cells and normal cells will be between 1 and 2, and it basically measures the complexity of the tissue structure of the biopsy specimen, and so the higher the number that they figure out, the more abnormal the tissue is. So if you had a cell with a dimension of say 1.934, etc., that would be a very abnormal cancer. That would be an abnormal cell, so it would be a cancer cell. But if you had one with a dimension of like 1.13, that would probably be a normal cell. And it makes figuring out whether a cancer cell or a cell is cancerous, it makes it a lot easier to figure out.
So another example for fractal dimension is the breathing coastline. So if we connect each point in unit of 200 kilometer, and it's not like really precise like how you calculate the coastline. And if you break into 100 kilometer like per part, it's like a little bit like better. And then if it's 50 kilometer, it's like you can see you like basically can calculate like the length, and okay. And this is the formula for calculating the length of the coastline, and we still need to use the fractal dimension.
So these are some examples of fractals in nature. So you can see that a lot of different things like flowers and fern leaves, you have the normal leaf, and then it keeps on branching off, and each of those littler leaves branches off and kind of goes on and on. You can also see it in things like parts of the Earth and also in the galaxies. You'll see that if you zoom in farther, it'll still look like the original galaxy, like that.
Okay.
Okay. Thank you.
Okay, questions?
So yeah, is there any questions? Yeah.
When you were doing, or for the, like figuring out the dimension of Sierpinski's triangle, I was wondering because you said it was like it was one triangle with 4 triangles inside of it.
Here.
Just go to the picture.
Yeah. Go to the.
Okay, wait here. I'll look up a picture of it.
Okay. So here.
Yeah. What makes like why is that? Why are there 3?
Like log 3 over log 2.
Or why is it log 3? Why are there only 3 similar triangles?
Well, because
So this is the original one.
Yeah.
And that one I show you, it's like that. And look, it's 1, 2, 3. There's 3 similar triangle inside of this triangle compared to this. This one doesn't count because there's like you can't draw one.
it's like compared to the original triangle, there are 3 things
3
inside that
similar
triangle that look
pieces.
like it.
But then why can't you use the smaller one?
This one? This
Or I
one?
mean because in each of those 3 triangles there's smaller.
Yeah, if you keep on going down and down, that
Yeah.
will increase the number because
But the
you'll have a
dimension
lot more
doesn't
similar
change.
triangles, but we just did it with this one because it's really hard to calculate once you get to
Okay.
a smaller amount. Okay.
But what Anita just said is the dimensions don't change. No matter
Don't
how many
change, so-
iterations you go,
It's
the
the same.
actual dimensions don't change. It's still a 3. It's still being divided by 3 every single case. Just do it over and over and over and over.
Yes, it's
Yeah.
still the same ratio. up and down, that's not going to be two-dimensional because it's not like a plane, but it's not a straight line either. So it has to be in between the two of them, and the same is true for planes and spheres. Any other
Very good explanation. Also, if you just think about, say, the bark of a tree, right? How many dimensions is the bark of a tree? Is it 2? It's sort of 2, but it's also kind of got a lot of, roughness to it, right? Well, that's the third dimension. So it's somewhere in between 2 and 3. And fractal analysis allows you to sort of get a pretty good idea of what that dimensionality is. You just have to have the idea that there is a possibility for something in between 2 and 3. And then fractal geometry allows you to actually measure it. Okay, thank you, girls. That was really good.